We're now in Algebra II at 9.1c, and we're going to talk about the symmetry with respect to the origin, and I have a couple theorems for you. If you become lost or confused during this video, just click on the description and watch the two previous ones to figure out what got confusing, okay? We can find examples of point symmetry in the real world. The bloom of a flower or a pinwheel show point symmetry. So for this flower, and I know it's a funny looking flower, but it gets the point across. So here's our line of symmetry. This point is symmetrical to this one through the origin through the center, see? And this one through the origin through the middle, and this one to this one. And same with the pinwheel. If we have this center point right here, we can do this point to this point and go right through the center, or this point to this point right through the center, see? And the concept of point symmetry can also be defined precisely in mathematical language. So I have a definition for you. 2 points, P and P sub 1, are symmetric with respect to a point Q when they're the same distance from Q, and all 3 points are on a line. So here's the pre-image, here's the image, the reflection, and going through Q here, it makes a straight line. See that? P sub 1 is said to be the image of P. A figure or set of points is symmetric with respect to a point when the image of each point is in the set. See? We got a straight line going on, don't we? So take a look at this one. The figure is symmetric with respect to the origin for this one. If we stick a pin into the origin and rotated the image 180 degrees, P and P sub 1 would swap places. They would be interchanged. So if I spin this around, I've got this taped to my spinner, the image is still going to look the same. Our squiggly snake-looking line is going to look exactly the same as I turn it, see? And these 2 points, P and P sub 1, swap places. And Q and Q sub 1 swap places, see? Let's see if I can do it like this, see? It's the same. These are pairs of symmetric points. The entire figure would look exactly as it did before rotating, and this means that the image of each point of the figure is also on the figure. This means that that image of P sub 1 is on the figure, see? Because when we spun it around 180 degrees, they interchanged. So take a look at these. These two are symmetric with respect to the point, and this one's not. If I have this point here and this point here, I could draw a line through the center point, see? And if I have this point here and this point here, I could draw a line through the center point. And anywhere on a circle, if I put a point here and a point here and go through the center point, it's going to be symmetric, see? But not with this one. If I wanted to have this point and this point go through this point, it's going to make a V. So this one's not symmetric with respect to the point, see? I can make a straight line going through the center with this one, or this one, but not with this one. I end up making a V shape, not a straight line. A circle, square, regular hexagon, these are some examples of figures with point symmetry. Going from this vertex to this vertex, I can make a straight line through the point, see? That center point. Or this vertex to this vertex makes a straight line. Or any vertex like this one to this one on the hexagon, see? Or this one to this one, I can go through the center point. And with capital letters, the alphabet, if we put a center point on each one of these and spun them around 180 degrees, the letters would look exactly the same. So these are symmetric with respect to a point, see? Symmetry with respect to the origin is a special type of point symmetry. So here's our first theorem. 2 points are symmetric with respect to the origin if and only if both their x and y coordinates are additive inverses of each other. The point symmetric to 3, -5 with respect to the origin is going to be a -3, 5. See how we've got the inverse of 3 and we got the inverse of -5? See? Here's our second theorem. The graph of a relation defined by an equation is symmetric with respect to the origin if and only if replacing x with the inverse of x and replacing y with the inverse of y produces an equivalent equation. So if we swap these, we're going to have an equivalent equation. So let's take a look at this second theorem. This gives us a way to test a relation for symmetry with respect to the origin when it's defined by an equation. If we have x squared equals y squared plus 2, we can test this equation. We could put in the inverse of x and the inverse of y, and because our new equation is equivalent to our original equation, the graph would be symmetric with respect to the origin, because it's equivalent. Negative x times negative x gives us a positive x. Negative y times negative y gives us a positive y. If we plugged in some real numbers, we could do 5 squared equals 4 squared plus 9. That gives us 25 equals 16 plus 9. Well, it's the same thing as negative 5 times negative 5 gives us a positive 25, and negative 4 times negative 4 gives us a positive 16. So this equation is true, and it's equivalent to the first equation. See? So we know that the graph would be symmetric with respect to the origin. See? All right. Our next video is 9.1d. We're going to talk about how to determine even or odd functions. I'm going to add this video to the Algebra II playlist. You can see the link in this description for Algebra I from last year, 12.4, about quadratic functions. And there'll be a link for those 2 previous videos that we did for this chapter, 9.1a and 9.1b. And we talked about symmetry of a line in those. So I hope this was helpful. If it was, please hit the like button so I know. And I hope you're having a great day. Don't forget I'm on patreon.com. And you can become a monthly supporter for just $1 or $2. It'll really help out my dogs and I with food and vet bills and stuff like that. And I'll see you next video. Bye.
Say hi, Bitsy.